which is also just memory. So the same concepts go. You have the address it starts at, and being that it's the same thing as memory, really the big difference is just the addresses. So we start at the offset of 800 and then just kind of start from the beginning, whereas with the stack, it's a higher address, but it's still just memory. The stack just gives you a different interface in how to deal with memory, and I'll go into more detail in a few slides from here, but the biggest interface is pushing to memory or pushing to the stack and popping from the stack, even though compilers heavily abuse that and don't do that as much. They allow you to access arbitrary data from the stack. So if there's any slide to take notes on, this would probably be the one if you want to start coding yourself. Typically, instead of like writing in Python or Perl, whatever, writing your source code and then just typing Perl and then the code, there's a couple steps to this. So you write your code in an editor, text editor, whatever you prefer. Then you'd run NASM on it, or whatever assembler you're using, so MASM, TASM, GAS, whatever. I like NASM because you can run it on both Linux and Windows, and I just like the syntax of it. I don't prefer GAS so much because it's the AT&T syntax, which is all kind of reversed in comparison. So I do prefer NASM, and then I use LD to do the linking, and then you can execute it from there. So mostly what's relevant in a 32-bit context on a 32-bit machine is the two commands down here. As an example, there's a lot of different things, a lot of different ways you can run it, but this is what I'm commonly doing when I'm assembling my code. Yeah, Joe?
Doesn't EDB internally use GASM instead of NASM?
No. No, it does the Intel syntax. It doesn't do the GAS or the AT&T syntax. What's that?
I thought when you install EDB, it requires you to install GASM by ASM.
I don't know, but I do know that the syntax that they show is Intel. Yeah, I don't know. Everybody ready for the next slide? So now we're going to jump right into code, starting with move, like I was kind of alluding to before. But at the same time going into how registers overlap a little bit, because that's like the first thing that kind of confuses people. But the move instruction just allows you to move data into a register. And as far as overlapping goes, AX, that register, is essentially just the last half of EAX. So if you were to like move something into AX, that does affect the last half of EAX. And then AH and AL, kind of the same thing, but for overlapping with AX, and again, EAX as well. AH would be like the high byte of AX, and AL would be the low byte of AX. And AX meaning like the accumulator register, EAX would be extended accumulator register. And when dealing with 64-bit, even though we're not talking about it here, it would actually be RAX for the 64-bit version of that. So this is some code, but really, let's just go over and look at it. I'm actually just going to open it up straight in the debugger here. And I'll zoom in. So to talk about the code real quick, I'm going to move 5s into EAX. I'm going to clear it. I'm going to move 5s into AX. I'm going to clear it. I'm going to move. This is actually 5-5. So you notice there's the 0x thing up here representing hex, but there isn't for the 8-5. 8-5 decimal is 5-5 in hex. So we'll move 5s into AH. We'll clear it, clear EAX, the whole thing, and then we'll move 5s into AL and clear it and just exit, just to show exactly what's happening to our registers over here. So I'm going to kind of tighten this up a little bit so we can kind of see everything. Okay, so I'm going to step once. We're going to run that first instruction. Everybody see that? The 5s got moved into EAX up there. And when something turns red in this debugger, that means it was changed. So we moved 5s into EAX with the move instruction. Next, we're going to move 0 into EAX. And there's a different way that compilers do moving 0 into registers, but we're just doing it explicitly this way because we're starting with just move. So we're going to clear it. It's going to turn to 0s. And now we're going to move 5s into AX, which in theory from that last slide should only move 5s into this last half of EAX. So I'm stepping again, and now we have 5s there in the last half only. I'll clear it again, and now I'm going to move 5s into AH, which should be the high byte of this last half, so it should be these 2 bytes right here. And now we got 5s there. And I'll clear it again, and I'll step one more time, moving 5s into AL, which is the lower byte. We got 5s in there. And did I clear it again? No, I didn't. So now I'm actually doing a syscall to actually exit gracefully, but we'll get into that later too. So did anybody want to see the code for any extended amount of time, like how this would actually look? This is a source code for NASM assembly code. This is what I wrote to be able to execute that in a debugger. Also in the booklet that was handed out, all of the code should be in there. Because I took screenshots of all of these slides and PDF'd it, so that's what got put in the slides there. So these things should be there too. This is essentially the same thing. So if you want notes for later. All right. This is a really, really simple command. It's exchange. So you can do the exchange opcode and then just specify the 2 registers. And without having to do tricky moves requiring a 3rd register, you can just swap the registers. So there's some code for it. We'll actually do it real quick. Just why not? So first of all, I'm moving some values into EAX and EBX just to get them populated, so then I can show you the exchange. So I'll step 2 times. Stepped once, we got 5s in EAX. I step again, I got 7s in EBX. Whoa. Okay, right there. And then I'm going to do an exchange. So what you should see is EAX and EBX just flip. So I'm stepping right now, and they flipped. That's all there is to that one. So let me refresh this a little bit.
Does that exchange actually have a temporary register in the background? You just don't explicitly create it? Or is it?
It shouldn't, but I don't know. I know what it does, the results of it, but I don't know what it does in the back end. So we're going to go through the stack a little bit, how it's supposed to be used with push and pop. And this is kind of a visual metaphor, but usually I don't like visual metaphors. Like they're a cool crutch, but I want to get to the bottom of what's actually happening. Like maybe not the level of like how it's really being implemented by like transistors and stuff, but like seeing it in the debugger, seeing what it's actually doing. But so our scenario we're dealing with here is we have the 3 registers EAX, EBX, and ECX with the values there in blue. And what I want to do is I want to reverse them. So in other words, I want EAX to have Fs, EBX won't change, and ECX would have the 5s. And I can do some tricky moves, but I can also push some stuff to the stack and pop it back from the stack in a way that makes it easier. So the stack, the most common metaphor people use for the stack is it's like a stack of plates in a buffet. You can push plates to the top of the stack, and you can pull plates from the top of the stack, but you can't do anything from the middle of the stack, which the analogy falls apart because of how people build stack frames and use the base pointer to do that. But this is just the simplest way to use the stack. So visually, if we push EAX to the stack, we get it on the top of the stack, and then we push EBX to the stack. So now it pushed the 5s down, and EBX, or the value that was in EBX, is at the top. And then we'll push ECX, and keeps on pushing them down. And now we'll just pop them back out in the same order of registers. So we're popping the value from the stack, which happens to be Fs, into EAX. There it is. And then we pop again to EBX, then we pop again to ECX. So we'll actually look at that running. And code for that is first 3 instructions, I'm just moving all those values to the registers. Then I push them all, EAX, EBX, ECX, then I pop them all, EAX, EBX, ECX. That's all we're doing.
Can you pop it to whichever one you want?
Yeah, and I mean, so all the general purpose registers, I haven't tested with some of the weird ones. Like there's a really weird, and I don't know if maybe I don't get into detail with this, but there's a really interesting thing where EIP, the instruction pointer, you can't actually, it's a move instruction, not pop, but you can't actually move it into a register. But what some people do, and you'll see this in shellcode, well, I'll get into it later, but it's a weird trick where you call to the instruction like right after that call, which is something you would never do, but it allows you to get an EIP on the stack, which you can then pop. It's interesting. But this is the same code that we saw in the last slide. One interesting thing is you see the 5s, you see the dead beef, but then you see -1, whereas I was doing Fs. So this is just a 2's complement representation of the data. You'll see over in the machine code here, B9 is like machine code for move to ECX, and then what follows is the values. So in this case, it's Fs. This is just how to represent it in 2's complement. So this is the debugger representing it for us. But you'll see when I step through these 3, which I'll do right now, I move the 5's to EAX, dead beef to EBX, and then Fs show up in ECX. So that's what's happening there. I'm going to kind of resize this a little bit so we can see the stack a little bit better. Okay, so really we're only going to be noticing these 3 lines of the stack here. Is that big enough for everybody? Okay. So first of all, I'm going to push EAX, which will be the 5s. So I'm doing that right now. And we see the 5s show up on the top of the stack there. Kind of like the visual picture in the last slide. And then we're going to push EBX, which contains dead beef right now. And see dead beef shows up at the top and pushes the 5s down. You'll notice that it doesn't actually remove the values from the register, though. And then we'll push ECX, which is Fs, so we push that down the stack, and Fs show up at the top. So we pushed everything to the stack, and now we can continue to pop them all. So we're going to pop EAX, which is this instruction here, which the stack contains Fs, so if we pop EAX, it just takes the top of the stack and puts it in EAX. EAX right now contains 5s, but being that the top of the stack is Fs, we should see it contain Fs when we do that. And now it does. And then we do pop EBX. So EBX contains dead beef. The top of the stack is dead beef. We should see nothing change when we do that. And we saw it stay at dead beef, but it did remove that value from the top of the stack. And then we'll do pop ECX. So ECX contains 5s. ECX should contain 5s after we run that. And that's the stack at its simplest. Compilers do a lot more with it, but that's what the stack is generally supposed to be used for.
Does the register EBF actually change and the debugger didn't highlight it because it didn't? Does it actually replace it? Does it do a compare and then not replace it?
No, it doesn't even look to see what it was. It just, I mean, really, technically, it did move dead beef to EBX, right? But
it doesn't change it. The debugger didn't actually.
Nothing changed. Yeah, so it didn't turn red because the value didn't actually change. Right. Yeah. I mean, it's still, on the hardware level, like, it absolutely moved dead beef to that register and thought it did, but, you know, the debugger is not displaying anything because, yeah, nothing changed. We can actually go through this pretty quickly, but basic math, I mean, it's pretty useful. So there's more mathematical operators, but like I said, I'm really going through like the 5–10% of the stuff that you use most of the time. So add, subtract, multiply, divide, increment, decrement, those are all pretty useful, right? So this is the code that we'll be going through. So there's a lot of moves, but in order, like we're going to be adding, we'll be subtracting, we'll be multiplying, dividing, decrementing, and incrementing. Or incrementing, decrementing in the order I did it. So first thing I'm going to do is move 5 into EAX. EAX now has 5. So then we'll use the add instruction, and we're adding and we're applying that to EAX, and the value is 3. So literally we're adding 3 to EAX. So any guess as to what EAX will be after I run this? Yeah, okay. So I'm stepping, and now it's 8. It's that simple. We're going to do sub EAX 2. So the value after we run this, EAX should then contain 6. Now it does. And now we're going to move 3 into BX, which, so not EBX. BX would be, again, that last half. It's that thing where I was saying that the registers overlap, that's not just for EAX, that's for more than just that register. So the same kind of pattern goes. BX would be the last half of EBX, so we're moving 3 to it. So we should just see 3 show up in EBX. And we have that there. So now we're going to do the multiply, and the reason we moved a value into the B register is because with multiplication and also division, it uses that register as well. So what we're really doing here when we say multiply BX is it actually implicitly takes EAX, divides EBX from it, and then stores the resulting value back into EAX. So I said divide, I meant multiply. Okay, so 6 times 3 should be 18. But this is hex, so it's not going to be 18 when we do it. We get 12. And that actually is 18 in decimal. Because the 1, that's like the 16th place, or the 16th place, so 1 that takes 16, and then adding 2 to that, that would be our 18. So that's what's actually happening there. Might look confusing at first, but that's all that is. And then we're going to move 5 into BX. So now we have 12 and 5, but really 18 and 5. And then we'll do division, which is similar with the way it uses the BX register. So 18 divided by 5 should be about 3. So we get 3 in EAX, and then EDX gives us a remainder. And that's kind of the interaction with all those registers. So now we'll get into increment and decrement. We'll increment EAX, so really going from 3 to 4. 3 to 4. Then we'll decrement EAX, so 4 to 3. Just increments by 1, or decrements by 1, that's all that does. So we're done with some basic math there. Any questions on that? Cool.
So does it always store the remainder in EDX?
Yeah. So I think it depends on when you have bigger values, I think it concatenates a couple registers, and honestly I'd have to go back to the Intel manual to look that up. Because yeah, divide and multiply, it even messes me up sometimes. So. That I don't think so either, just because if you're if you're taking a very large value dividing from, like, or same answer I just gave him. Yeah, I don't know. I know for smaller numbers it works exactly like that, but looking at the manual, I do know, like, I see they concatenate a couple registers, like they put like a register and a colon in another register, and that's dealing with more than one. So yeah, now logic, and actually, so I made some, I have some code for that, but it really, I'm not gonna run this unless anybody wants to see me run it, but like, seeing the values change, unless you're seeing it in binary, it really doesn't make a whole lot of sense. So I don't think you can get EDB to show you the registers in binary. But I will explain them a little bit. And yeah, the basic logic stuff, so AND, OR, NOT, and XOR, which XOR you can build out of AND, OR, NOT, but you get a convenient XOR. So yeah, I'm moving values into AL, like AF, I always move into AL before I do my logic operator, and then I'm always doing the logic to 1C. It's just either AND, or I'm doing OR NOT, which doesn't take another value, and then exclusive OR. This isn't so much about assembly anymore than it is about logic, so just real quick, and you do it bit by bit, like so. I almost feel like walking over, but I probably won't. When you take the leftmost column, so you have this 1 here and this 0 here, for the result, which is this bottom value, both the first and second value need to be a 1 for the bottom one to be a 1, and that's what AND means. So this is a good example of how it does work, 1 and 1, so we do have both values being 1, so the result of that column would be a 1. Same one with this column, but then you get to this column, only one of them is a 1, so the result is not a 1. So these 1s and 0s do represent AF, these 1s and 0s represent 1C, and then the result in hex would be 0C, because that's what the 0, and then this represents C. Or the case with that is one or the other needs to be a 1 for the output to be a 1. And that is also inclusive. This is implicitly inclusive OR. So one or the other is technically 1, so our output can be 1. So if we did an OR on AF and 1C, the result would be BF. Not just flips all the 1s and 0s, that's all it does. So if it was a 1, make it a 0. If it was a 0, make it a 1. So AF gets converted to 5, 0. And then exclusive OR is one or the other, but not both. So that's, instead of implicitly inclusive OR, it's actually exclusive OR. So in the case where we have both of them being 1, they can't actually produce a 1. Does anybody want to see the code running for that? I mean, I can. It doesn't matter. It just doesn't really. You'll just see those values showing up. So I'll take that as a no. Now we'll do some shifts. Also another binary operator. We can take bits in a register and shift the bits, like literally shift the bits, like to the right or left, and then we can also rotate them. So shifting the bits, instead of like pushing them off, they actually rotate back into the back end of it. So there is some code for it. Like you can actually shift by more than one value. So instead of shifting like one at a time, you can say I want you to shift it 4 times through. So talking about shift left or shifting bits to the left. Say we had this binary in the AL register, and in decimal and parentheses I have, that means 2. But this is the bits. So if we wanted to say shift to the left on the register AL, and by 4 times, that means everything got shifted to the left, like left. So you see this 1 got moved over by 4 places. And if we shift, it would all be zeros, because that 1 would have been just shifted all the way out. So a cool thing or a neat thing I think about shifting is shifting to the left specifically can act like multiplying a little bit, and shifting to the right would be kind of like division. But each time you shift to the left, it's like multiplying by 2. So we shifted to the left by 4 times, so it's like we multiplied by 2 4 times. So this value here is 32 in decimal. So 2, and then times 2 times 2 times 2 times 2 would be 32. And that's really useful. Like even with the compiler, if I literally said, hey, multiply by, like this in this case would be 16. If I said multiply by 16, the compiler would not do a mul instruction. We have a mul instruction, but the compilers, most compilers these days, would actually just do a shift left because it doesn't take as many clocks to do it. And if you're hand coding assembly, that's something to keep in mind. It's quicker to, if you know you're multiplying by those increments, then shifting is a lot more useful. Shift right, same kind of deal here. So I start with 32 this time. I'm shifting to the right only by 3, and that'd be like divide by 2, divide by 2, divide by 2, 3 times. So we start with this value here, and then the 1 gets shifted to the right 3 places, and this would actually represent 4. So 32 divided by 2, divided by 2, divided by 2 would be 4. And then rotating, like I was saying, instead of pushing them all out, they get pushed back around to the back end of it. So I'm rotating to the left by 3. This 1 moves, this place, this place, this place, and then finally this place for the 3rd time. So that's why we get this result down here by rotating to the left by 3. And then rotating the right, same thing, just the other direction. Any questions before I get into conditions and jumps?
Yeah.
Yeah.
So if you're shifting left, like let's say in AL, and you shift it past AL, will it go into AH?
No. Well, wait. Yeah. Right. Absolutely. We can try it.
No, I'm just,
But yeah, it should.
and then so on and so forth, like EA, EAX.
Right. And then RAX if you're 64-bitting that. I mean, I'm saying in theory, but I haven't tried it, so yeah. But yeah, it should. Okay. This is definitely not all the conditional jumps, and not even all the ways to check conditions. Like the first few lines of here, this is jump if less than, jump if greater than, jump if equal, jump if not equal, and then just jump anyways, like no conditions. And then compare is a way to compare values. But although it exists, I'm not going to go over. Test is another really common one. But there's even more than just compare and test. Just compare and test are used the most commonly. But compare is implicitly like subtract. It just doesn't actually subtract the values. It sets some flags. Test is implicitly like and, but it doesn't actually do the and. It just sets the flags that would be set by that. And we'll get into some of that. Here's some code. It's really like kind of convoluted, but I just kind of wanted to show a lot of different conditions. So I'll kind of explain the code real quick before I step through it. So first I'm going to be moving 5 to EAX. And then I'm going to be comparing EAX with 5. So in other words, like, you know, it's kind of like in a high-level language, like, does EAX equal 5? And then jump if it's not equal. And we're setting a label. We're jumping to start, which is up here. Which we necessarily would not, because if I'm saying jump if they're not equal, well, they were equal, so we fall through. And then we compare EAX, which is still 5, to 4, and jump if less than. So we're really saying, is EAX less than 4? And in that case, it does jump down to next, and now we compare to 6, jump if greater than, and jumping to another. So we jump down to another, and then we just unconditionally jump to next, which is up here. So then we get into an infinite loop. And just so you know, I should actually show this. Even though I say these labels like start and next, the assembler will actually convert this to actual addresses. So noting that start is the start of the program, and I say jump to start, what's really happening here, instead of just start, it's saying jump to 48060. Well, there's this 8 here, but I'm just looking at the last remaining here. So being that the program starts at this instruction here, we have our 48060. So it's just replacing those friendly names with real addresses. So it's doing the exact same thing. Yeah, this one's going to be kind of like, I'm going to try to zoom this as tight as I possibly can so we can kind of see everything here, because I kind of want to see our addresses up here too. So we're going to move 5 into EAX here and compare EAX with 5, and that actually sets some flags. I wouldn't say it's super complicated, but it takes some time. But we have flags for like carry. We have a 0 flag. In this case, the 0 flag is pretty relevant. But if we do a subtract 5 from 5, the result is 0. So it sets a flag for 0. And that's actually how our conditional operators actually work. It's saying jump if not 0. When it says jump if not 0, it's literally checking the 0 flag. So when I compare EAX with 5, which I'm doing right now, that Z goes capital there. So now when I say jump if not 0, it knows to check that flag. Also notice that I said jump if not 0. In the case here, I say jump if not equal. That's logically the same thing. Okay. So we're going to do the jump if not 0, which just means we're going to fall through to the next instruction. So this green arrow will just go down 1. And then it did. So now we'll compare EAX to 4. This 0 flag should probably clear. And so now it's lowercase again. So we're actually gonna jump, and it says jump to 4806F, which is 4806F, the next instruction. So that's what it does. And then we're gonna compare to 6. And in this case, this condition will also turn out to be true. So the 74 address, which is also right there. And now it just says jump. It doesn't check the conditions at all. And jumping is to the 4806F, which is up here, just up to instructions. So we end up there, and nothing changes after this. So I can keep on executing, and now we're in an infinite loop. So in assembly, just to kind of sum up, we can jump to a label. We could have also like literally said jump to this address, but you don't always know where you're going to be in the address space, so sometimes it doesn't work. Sometimes you do know where you're going to be, and you can hack around that a little bit. And then you have relative jumping. So this is like based on where this jump instruction ended, relative to that, where do I jump to? And it's assigned value. So 0, 0 all the way to 7F is like 0 through 127 is as far as you can go forward. And then if it starts with 8 all the way up to F, that's actually a negative value. So FF would be -1, FE would be -2, FD would be -3, and so on. So you can have all the way up to negative 128. So like jumping to 128 bytes before that instruction. This one's a funny one because jump itself is a one, like that part of the opcode is 1 byte, and then the operand, which would be this FE, is another byte. So it's in full a 2-byte instruction. So jump FE would be jumping -2. And being that it's a 2-byte instruction, that literally means jump to its own instruction. So it's kind of like a funny joke. Some of us like, you know, it's the, is it EBFE? Joe, you know this one? EB? Yeah. And then just some examples of compare. So call and return. If any of you are familiar with high-level languages, it's it's kind of like a jump, but it allows you to know where to come back to. So it's kind of like calling a subroutine or a function or whatever. So when you do call, consider it like jump. It jumps to some code, but when you're done with that code you jumped to, you can use the return or ret, and it'll actually go back to the instruction right after you did call. And this, I am going to step through this one because this one's really interesting. The way I wrote this code is kind of fail. It's really funny because of calling ret without knowing where to go back to. But in general, the first time it works, so I'm moving 5 to EAX, which the moving doesn't matter so much, but just, you know, 5 goes into EAX. Then I'm doing call to other code. So it skips past this part and jumps right to other code. And then I move 9 into EAX. And the only reason I'm moving 9 into EAX is so you know 7 didn't get moved to EAX. You know that it actually skipped that. And then I do a return. So then it'll actually return right after the first call. So now we're at the move instruction, and 7 gets moved into EAX. Now where it gets funny is that we keep moving, and now we're back down to other code again. We move 9 into EAX again, and then we return, but we didn't call. So I'll fully explain the weirdness that happens because of that. This kind of goes into a little bit more lower level of how call and return actually works. Or my debugger will freeze up, so I'll kill that real quick. Whoops. Okay. And by the way, this is just a Linux Mint 32-bit VM. But I had to install NASM, which is actually just a sudo apt-get, and I had to also install EDB, which is not just a simple sudo apt-get. It has some dependencies, and I forget if you build it from source, but maybe you don't. But if you want to get going even quicker than that, I do know that Kali comes with both out of the box. So what we're going to go into here is how, when we do a call, how does it know where to come back from? That's exactly what we'll talk about here. The answer is the stack, spoiler. So we're going to move our 5 into EAX. We have 5 there. Now we're going to do our call, which is to the 4806F, which is this instruction 2 instructions down, the move 9. So right now, the instruction after the 6F, because that's where we want to jump to if we do a return, would be this one right down here. I'll zoom in quite a bit. It would be the 48065, right? So if I step, what's going to happen is the address of this will go into the stack down here, so we know where to come back from. That's how it keeps track. So I'm going to step one time. We're going to go down to the instruction down here for move 9, which I'll do. I'm stepping right now. So we did jump or call down here, but in the stack we have the 4806A, which is the address of this instruction up here. So now we know where to come back from. So I'll move 9 into EAX, so we have 9 in there. And then I'll do my return, and return literally goes down here and says what's the value on the stack, pops it off the stack even, and we jump to that location as well. So I'm going to step it, and now we're up there at that address, and now it's no longer on the stack. So here's where it gets funny. If we keep executing, we're going to move 7 into EAX, which we have. Now we're going to move 9 into EAX, which we have. And now we have return again. And remember, return looks at the value on the stack and jumps to it. So what memory location are we going to jump to here? 1. So I'll execute that. Oh, crap. Crashed. So that's kind of cool. I mean, this is just a slide explaining what we just walked through. This has got to be the simplest instruction ever. Yeah, no operation, no op, or nop. There's some code. Nop, nop, nop. Okay, let's just jump to start. It's really important people understand nop. I'll have to show it because it's so complicated. So, remembering that values that change here turn red. So I'm going to step. All right, all black, step, step. Really the only thing that stays red is the instruction pointer because that is changing. We are changing our instruction. Again, nothing. And then we jump to the first instruction. So we got a good do nothing loop here. Nops are like one stupid way to use a nop is for timing, like if you want to pad some time. Another reason to use nops is for actual literal padding, like the stack is by increments of either 4 bytes or 8 bytes, depending on 32-bit or 64-bit. If you're actually doing shell code stuff and you wanted it to be aligned, or you're running it from the you're running code from the stack and you want it to be aligned, that could be another way to do it. And there's also the knob sled, which I really don't care about, so I'm not going to talk about that. So it's kind of one of the last topics I'm going to go through for actual assembly. Then we'll get into some kind of cool stuff, which I think there's time for. Yeah. So memory and system calls, and there's a reason I'm doing them both at once, even though they're completely different ideas. A system call, and it's different for Windows and Linux, but it's essentially calling the OS, saying, hey, do something for me. I was almost in every sample program I've done so far, I was doing a system call. At the end, I was saying, hey, Linux, can you exit for me? So that typical system call in Linux is doing an interrupt, and the value put in that interrupt is 80 in hex, so that's in int 80, and that just all alone just says, hey, like Linux, do something. As far as what you're telling Linux to do, it all depends on what you have loaded up into the registers at the time you're doing the int 80. So the most common one for exit is just loading 1 into EAX, and then if you did an int 80 while EAX has 1, it'll exit. And I'll do a couple other, like as far as printing to the screen, we'll do that one. And then in Windows, you know, API calls are a little bit different. I don't even, yeah, it's like I think you just do a call. I've done a lot more assembly on Linux than Windows, though. Like the only assembly I've really done in Windows is going through like this Grem reversing course, and that was all pretty much Windows based. And then, well, this is the noisiest one here, but it's actually pretty simple when you break it down. The only reason I'm using memory heavily is because I'm going to be doing a system call for writing something out to the screen, and that system call you actually have to, as far as what you want to write to the screen, well, it has to be somewhere in memory, and you have to point it to where that starts in memory. So this first huge chunk here, all I'm really doing is loading memory up with hello world. Like I'm moving some values into EAX, and then I'm moving that what is in EAX to a value in memory. So like some memory here is just like I allocated some memory, and the assembler just translates that to an actual address of memory, and I reserved 16 bytes of it. So this is the NASM syntax of how to reserve memory. So it's like starting at some memory and then adding an offset of 12. C in hex, 12 is decimal. So moving this, I guess this would be, what do I got here, 0A, 21. So this is, the 21 is an exclamation point, the 0A is like a carriage return, and I'm moving all this in reverse is because Intel is, was it little endian? I don't know, it's like I always call it reverse endian because it doesn't make any sense. I learned assembly on Motorola, which actually makes sense, so just know when you deal with memory, stuff will be reversed. So I'm literally moving hello world into memory in reverse. So like this 64, 6C, 72, 6F, that's like the last part of world for hello world. And I'm only incrementing by 8 this time for the memory offset. And I'm just, like I said, moving hello world into memory reverse. And that's all this big chunk is doing here. And then after that, I'm doing a syscall for write. So notice at the very end, I do int 80. I'm calling the kernel in comment line here, invoke the penguin. But for means write for EAX, but you still need more than that. So ECX will actually point to where you want, where in memory the text actually starts. And then EDX is how much you're actually writing. So in this case, 14 bytes is how much we were writing. And then EDX is or EBX is just more specific. It's going to be the standard out. And after it writes that, then we do our getting EAX loaded with 1 and calling the penguin again, and that just gracefully exits. So I'll run this one, and we'll actually look at the memory down here this time so we can watch it get loaded up. Not liking me. It's kind of an art to be able to see everything here. Just a little bit. Okay. Cool. Okay. So this is us moving the 0821 into EAX. We're going to do that real quick. So that's now an EAX. And now we're moving what's in EAX to this memory location. So it's 80490D4. So in memory, here's our 80480D4 or D0, and then so this would be 0, 1, 2, 3, 4, yeah, 4. I think. Anyway, we'll run it. So we should see that hex show up there. Or actually, this is the executable memory. Let me. It's in a different memory region. Okay. So yeah, here's our 0821 right there in memory. So now we're going to move some more stuff into EAX. We have the 64, 6C, 72, 6F. That's the end part of world. And now we'll move it into the starting offset of D0 of memory, which is down here. So you should see this 64, 6C, 72, 6F. That value show up in memory down here. Yeah, it's pretty small, but I'll do it, and then I'll zoom real quick down. That's the data that actually showed up there. And if I scroll over to the hex, see how it's starting to build that string out for us. Okay. So I'll just step it a few more times, watch it build out hello world. So hello world is in there. And in memory, you can see it shows up kind of in order. Now we're going to move 4 into EAX. We're going to move the starting location of C8, which is C, and then 8 was around here, so this is where the hello world starts in memory. So that's what we're doing with that. So now we have that address, and the debugger even kind of nicely tells you, hey, this is a string that's in there. And then we're saying moving 14 into EDX, which is saying 14 bytes, and then moving 1 into EBX, which is saying standard out. And we invoke the penguin. And let me, I think in the terminal, it actually showed the hello world over here. And to zoom back in, now we're just moving 1 into EAX. And we can do our int 80, and it exits from the program. So we're kind of done with all the basic assembly stuff. Now I'm only going to go through one example of this, but it's just a general strategy of like, okay, there's a little bit of assembly, but you probably can't make really cool applications at that point with just the basics. But again, 75 minutes. I try to pack the most important stuff, what I thought was most important stuff in that amount of time. So for all the extra stuff, what I'd recommend doing is, if you're familiar with C, would probably be the best bet. But if you're familiar with C, write something in high level, which is C, compile it, and see what it produced. And I would say, this is just my opinion, but C does allow you to do an intermediate assembly step, so you can see what assembly it produced. But it's in the AT&T syntax, not the Intel syntax that NASM uses. It's like the gas intermediary, like GNU assembler. So I don't really care about that. I just straight compile it, and I look at the binary in a debugger or even a disassembler. Like in the case of Linux, I like Boken, but I mean, if you're doing it in Windows, you can use whatever assembler you want for that, or disassembler. So here's kind of an example. I want to know how assembly or how a compiler thinks to do a while loop in assembly. So this C code is just initializing a variable, saying while that variable is less than 10, print it out, increment it, and when it's no longer less than 10, the program's done. So how would that look in assembly? I compiled it, and I kind of had to highlight some stuff. This is EDB, but it looks kind of like crazy until you really look at it. So on the side, I showed the C equivalent stuff of what's happening here. But so we're looking at ESP plus 28. Just look at that as I should just go back to my other slide. Look at that as our number variable. So anytime you see ESP plus 28, that's number. So we're moving 0 into number. And then immediately we're jumping down to something else here. So we're jumping down to this line of code. So this is our while number is less than 10. So we're comparing number with 9, jump if less than or equal to. And this is the address that it's jumping to, which happens to be our print statement up here. It would be jumping to up here. All of this code loads that value, the number, and then does a call to printf in this case to print that value out. And then it drops down to this instruction, which is in C number plus plus. In this case, it's just add, and then the number 1. And eventually, it's going to fail this compare and not jump, and then it'll leave and exit that part of the loop. So really, looking at all these instructions here, I would say I don't think there's any instruction here that I haven't covered previously. So you can use like the basic knowledge of what I previously covered for assembly, and if you want to learn something new of how higher level languages do stuff, you can build on your knowledge this way. And this is just an example with a while loop. Like in C, I really could have done some cool stuff like multiplying by 16, right? In C, it doesn't do a multiply instruction. It does like a shift. Or another cool example is moving 0 into a register. In this case, it wasn't a register. It actually did a location. But if it was a register, it would actually do not move 0 into a register, but exclusive OR the register with itself. Because if you exclusive OR any register, or if you exclusive OR any value with its own value, the result is 0. And the reason that compilers do that is because moving 0 into a register, like legitimately doing it, is about, I think, 5 bytes of machine code. But XOR a register with itself is 2 bytes. So naturally, a compiler is going to do the 2-byte thing that does an equivalent operation. So if you were to ever reverse code and you saw an XOR 0 with it, or a XOR a register with itself, it's probably just moving 0 into that register is the intent. So what if assembly is too high level? Because I've actually run into cases where I have gotten that feeling where assembly feels too high level. So if you want to program not in assembly, but if you want to program in machine code instead, there's a couple resources. One of them, one that I haven't written myself, it's called shellcode to exe. It's a Python script. That's for if you want to do Windows stuff, so the PE files. I couldn't find anything like that equivalent on the Linux end, so I wrote my own script called m to elf. It's a Perl script. It parses hex, and also, if you really want to, it parses 1s and 0s. So you can literally fucking write in 1s and 0s. You can write code in 1s and 0s. It's pretty cool. And it has a couple other things, like you can set its own code to executable, which by default is not something that happens. So when I'm looking at shellcode and I actually want to step through it, I can just copy the hex from it and make it an elf executable file. And some shellcode needs to be self-executable or self-modifying, actually. But normally you can't modify your own program by default, so this allows you to do that as well. I prepared a quick little video of doing that with the shellcode from the stack, or the smashing the stack for fun and profit. It'll get less blurry in a second here, but this is just, I'm on frac.org right now. I scrolled down to the shellcode, so we're looking at the shellcode up at the top there, and I'll start playing the video. So I'm highlighting the shellcode, and now I'm pasting it into Sublime Text, doing some quick little find and replace for, removing the quotes, and then I'll remove the 0x, the /x convention, so all I'm left with hex. And now this pesky little bin sh thing, which that's the funny thing, it's shellcode. It's actually calling at the sh shell. So real quick here on the terminal, I'm echoing out bin sh just so I can get the hex real quick. Just a quick little hack to get the hex. Do an xxd for the hex dump. So now I got the hex for that. So in my text file here, I'm just going to replace the bin sh with the actual hex. Then you see me prettying it up a little bit, which really doesn't matter too much, but I just want it all on the same line here. So that's the same shellcode, just straight hex. Now I'm going to save it. I just called it machine.m, but or did I? No, I called it shell.m. The extension doesn't matter, but I called it shell.m. And then my Perl script, --in, so the in file, shell.m, out, I'm just going to call it shell. And then I also do a write over, which makes it self-modifying, which matters for this one. Making it executable. And then I run it. And now I got shell. So it's actually sh, not bash. So I exit, now I'm back to bash. So I took that hex and I made it so I can execute it. And then in the debugger, there it is. And just to end the video, I just kind of compared them, lined them up, so you could see, like say with this shellcode on the website, you see the EB1F, 5E, 89, whatever. In the actual code here, you see the EB1F, 5E, 89, 76, the same as the shellcode. It's just literally translating that to actual executable code. So on my GitHub, I actually took all that machine code and I commented that. So, and yeah, my script does allow for comments. In this case, I use the # because I'm a Perl guy. So each line of machine code I commented out, or commented, so you can see what it's actually supposed to be doing. Like syscalls are used. They do that tricky call, and they also do a syscall for exec, and it points to this bin sh part down here. So it's doing an exec of bin sh. So it's kind of really cool as a learning exercise for me, like to look at shellcode and to be able to, instead of just like disassembling it, which I could do, I can actually step through it safely. Like probably do it in a VM, but I can step through it and see like in the debugger what's actually happening, and to me that's great. So I think I actually went through that pretty quickly. So there's plenty of time for questions. Joe? Okay, so he was saying that if, for the people I didn't hear, and also I guess for the video, in OllyDB you can take that shellcode and paste it into memory, right, and then execute it. Yeah, and actually on top of that, I didn't think about that, but you could probably do a dump too, right? And then you can actually just have that as a file as well to execute from. Yeah, so that's a pretty cool strategy. Although that is Olly, not EDB, but on the Windows end, yeah, you could do that. That's pretty cool. I mean, I can like run through some more code, make some more code. I can do whatever. Yeah. 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 Do you want me to? I could run through it again, or is there something specific?
Were you able to actually get the EP address, or?
Yeah. Oh, yeah. Okay. Like, I really do have enough time, so I can actually just start coding that right now, so we can. Okay, just a second. I'm used to using on the Mac the command stuff, but now I'm in a VM, so it like gets all derpy. Yeah, full screen. Okay. So I'm going to do a call. and actually I got to set a label. So I'm going to call this just next. This is the instruction it's calling to. And I'll just, throw a nop here, whatever. So I really want to call to next. And actually, no, not a nop. So what we'll do is we'll pop EAX. Just pop EAX. So this code sequence here is what gives us EIP. And I'll run through it because that looks a little bit weird. But so I'll save this real quick. I think I literally, yeah, no. I think I actually compiled this before, but I'll do it from scratch again. So get EIP.asm. Yeah, sure. That a little bit better? Or, I actually, yeah, I'll just move the terminal up. It's probably what you meant, but... Okay. So this is me just running NASM on that get EIP. And then I do LD. Cannibalizing the last time I ran that command. Cool. Should be it. So now I'll open it up in the debugger. Okay, yeah, this looks like it's going to be good. Just crunch this all in here so I can zoom in as far as possible because we want to see the stack too. Who cares about the memory? Okay, so on this first instruction here, we're going to do a call to 6.5, which is this next instruction here, and then we're going to pop whatever's on the stack to EAX. EIP right now is 6.0, so it should actually push 6.5, this one. So call, it's the next instruction into the stack. So I'm going to step once, noticing that the stack has 0.1 right now. It's like a lot of stuff moving at once, but step once. So we're on the next instruction. The stack now has 6.5 on it, the 8048065, which is also EIP right now. And then we're going to pop. So I do that right now, and it should give us that value, that address now in EAX. And we have it there now. So like that might not seem that fantastic or anything what we did there, but the point is, and I'll actually do this too, we cannot do move. So move EAX, EIP. We can't do that. And I'll go ahead and save this. Yeah. Go back to the terminal here. Yeah. NASM throws a fit. You just can't do that. So if your code for any reason wanted to know where it is, where its instruction currently is, that's the cool trick to do that. There's even IDS signatures that look specifically for that code sequence, which is kind of funny because like I've actually used that sequence legitimately before. Where I work, I made a little challenge for my team for assembly, and the whole challenge was like within the debugger. Like all the questions that it asked were within the debugger. And one of the questions was, what is EIP right now? And the only way for me to know that as a program is to do that little trick. In fact, what time is it? Yeah. I'll show you that in the debugger, that little challenge. There's nothing work confidential in there, so it's okay. first have to find where I saved it to. You know what, I might not even have it on here. Too bad. But it was kind of funny because the questions, they would show up in memory. So I'd like blast into memory like ASCII of what the question is, and to answer it, you actually had to place the answer into EDI, the register EDI. Like you had to literally, click on the register and edit it, and then its own program would check that register with the answer that it thinks it should be, and it'll either give you the fail message or not. And I literally had to also do that hack where the you can write to its own program, because it was modifying its own program to get it to display into memory like that. And in ELF, there is a quick ELF hack. There's like 1 byte you can change to make it writable. So like I wrote the whole thing in assembly, but I actually like opened the program up in a hex editor and changed that 1 little byte in the ELF header to make it so it could write to itself. It's too bad I don't have it on me. I can spend the next couple minutes trying to look for it if anybody has any questions that they want to think of. Yeah, I don't know where it is. F it, whatever. Well, actually, I might even have it in my other VM. Let me close out of this one real quick. Another cool thing about machine code, there's more than one way to do it, and this is why I say assembly is sometimes too high level. Is say like XORing a register with itself, like 3-0, I think 3-0 is a XOR, but there's, if you were to just like run the Metasploit NASM shell and say, hey, what's XOR this register with itself, it'll give you an opcode, but there's like more than one opcode that does exactly the same thing, just because of how some of the addressing works. So there's like overlap on some opcodes. So there's especially with 64-bit and prefixing, there's many ways to do the same thing for some stuff. Yeah, I don't think it's in here either. Although, just to emphasize what I was just talking about, the first like 10 lines here, notice the assembly opcode here, XOR AL with AL, and notice the machine code, never the same. It's kind of funny. All right, yeah, man, that's all I got. That's thanks. Yeah.
You talk a little bit about the different debuggers and assemblers you use in your experience with them. In my experience, I've always found that GDB a lot less buggy than PDB. I don't know if that's true for your experience, if PDB's gotten a lot better over time. Also, I was wondering if anybody who uses IDA's debugger for Linux. I know IDA's debugger for Windows is not for JavaScript typically. That's what I use WinDBG on Windows, but
No, so, and Joe, you can like walk up here if you want to answer it on the microphone, but no, I haven't used IDA's Linux version, so no idea. As far as GDB versus EDB, I I've noticed CDB be a little bit buggy, and really the only bugginess I ever experienced with it is what actually was happening right now during this whole thing when it would sometimes just like freeze up. But it hasn't really been that big of a deal for me. I like the OllyDB look and feel to it, whereas GDB like it is more powerful, but like it just feels a little bit more like work. Um, um, yeah, and as far as the Windows end of it, I definitely use Ollie more than Immunity. As far as speaking of debuggers in general, um, but that's about it with my experience. Joe, you wanted to say something?
Linux version of IDA is fantastic. In terms of Windows for debuggers, it depends on whether you want to use a kernel debugger or a local user debugger.
Yeah.
For kernel debuggers, soft ice is dead. It's not coming back. But Sizer, if you can find it, SYSER, is an excellent replacement for personal VM. For 32-bit code, the best, in my opinion, is Immunity Debugger because it has a plugin for Python. The standard is still Ollie McGee, and it's the most maintained. Probably most crackers in the world still using Ollie there. For 64-bit, there's Unbug DB and Visual Tux. Those both work on Windows for 64-bit debuggers. There is yet to be a port of Ollie or Immunity for 64-bit. So that still kind of sucks. I think Ollie 64 is really good. And Hopper, have you played with Hopper at all? Hopper on matchbooks or on Mac and Linux? I have not played with Hopper. It actually is like a cheap form of IDA for disassembly, navigating disassemblies. It ties into debuggers. So does IDA, so I kind of see the point. If you can afford IDA, IDA is like
$99.
if you can afford IDA, IDA is hands down one of the best reverse engineering tools you can ever get.
I'd also say on the Linux end of it, I forgot to talk about disassemblers, but Bokken, Bokken, is pretty sweet. I mean, it's no IDA Pro, but or IDA Free even, but I use it pretty heavily when I want to see the code, but not because yeah, there's a safety issue in opening up any random thing in a debugger. So like if I just want to see the static code, I use Bokken on the Linux end. And yeah, I mean, if you have any other questions that you don't want to ask in front of a lot of people, you can always just feel free to find me. Um, I'm not that much of an asshole. Cool.
All right, we have about 12 minutes until the next talk, so feel free to refresh your coffee and snacks, and we'll get started in about 12 minutes. If anybody wants any, there's the yogurt things in the back. Yogurt granola.
I have one. That should work, hopefully. It's brand new. Haven't tried it yet. Our IT guy just came by and dropped it on my desk that you may need this.
Oh, yeah.
Yeah, good point.